Hello and welcome to Math 4564 Operational Methods. In this class, we'll look at Laplace transform, Fourier transform, and a little bit of differential equations and how all of those things are connected. The first third of the class will be dedicated to Laplace transform, and let's get straight to the chase. So, what is Laplace transform and why do we use it? To answer the second question, I suggest we look at two somewhat simple problem. You've seen this problem before. First of all, this problem is a simple second-order differential equation. We know how to solve it. It's non-homogeneous, so we have to use something like a variation of parameters formula. And if g of t has a simple form, then it's not a very difficult problem. However, what if g of t has a peculiar form? What if it's not a trigonometric function or exponential function? What if it is a pulse function that goes to 1, then to 0, then to 1, then to 0, and it's just a periodic function which jumps up and down? You can imagine a problem like that may raise an analysis of digital circuits. Trying to use the variation of parameters formula with this function may prove difficult. And this is where Laplace transform actually helps a lot in simplifying the problem and make it a lot easier to analyze. Another type of problem where the framework of system transfer functions proves very, very useful is analysis of problems where we need to do the inverse problem, where we don't know exactly the model of a system, but we can experiment with the system. So let's look at a very simple black box type problem. We have something that has inner workings of a spring mass dashboard system. We can apply any external forcing as we wish, and we can observe the system going up and down. And can we figure out what's going on inside? So let's assume that inside is just a simple spring, a dashpot for damping, which is just a cylinder with a piston. So the spring has a constant K, dashpot has a constant gamma, the damping coefficient, the whole thing has a mass m. So the question is, can we figure out the parameters K, m, and gamma after observing the reaction of the system to some external forcing? And this is where, as I said, the framework of system transfer function is very, very useful. And all of that will be discussed later. So how does the Laplace transform help us to solve this problem in a somewhat easier way? To best explain it, let's look at this graph. We have a math problem and we're trying to figure out a solution to some equation that takes time and the function y, maybe its derivatives, and creates an equation with it. So we're trying to find a solution. And a direct way of solving it may prove a little bit difficult. The Laplace transform does it in a slightly different way. It's like a detour. It transforms the problem into an equation for what we shall call y of s, And then the solution to this problem may be slightly easier to obtain. And the last thing we need to do is to transform back the function y of s into the solution y of t. So we need to apply the inverse transformation. So the question is it really worth it? Well, the answer is whether or not applying the transformation, solving the transform problem, and applying the inverse transformation, is it really easier than solving the problem directly? And sometimes it is. You can imagine it as sort of trying to get to the other side of the mountain. We have a shortest path, which requires us to bore a tunnel through the mountain, which may prove very, very difficult. And sometimes it's easier to take a detour, to climb the mountain, and then descend the mountain, and then we're on the other side. So let's give the definition of the Laplace transform. Suppose you have a function f that is defined for all t that's greater than 0. We define the Laplace transform of f as, and it's denoted by a script letter L, and this is somewhat awkward to write, so sometimes we're just going to write capital F of s, meaning the Laplace transform of little f, and it's this integral. We take the function f of t multiplied by e to the minus st, and we integrate from 0 to infinity. And if this integral converges, the resulting value is the Laplace transform for a given value of the parameter s. So what happens here is that the function that was originally a function of t, after the integration, t disappears, and what's left is the parameter s right here. And the parameter s is a variable for the transformed function capital F of s. So let's talk about this particular integration and what it means we have to do. Well, if you remember, we defined the integrals over the infinite intervals as limits of integrals over finite integrals. The reason we do that is because it's not possible to use fundamental theorem of calculus on these integrals, because the fundamental theorem of calculus requires a finite interval of integration. So instead, we convert the integral into an integral over a finite period that goes from 0 to, say, capital T, and then we let that capital T go to infinity. And sometimes this integral doesn't converge for some values of s. But that's not a problem for the Laplace transform. As long as this integral converges for some values of s, we say that the function has a Laplace transform. It's also interesting to note that we integrate from 0 to infinity. So whatever happens with the function little f of t before 0, when t is negative, that doesn't affect the Laplace transform. However, it is a convention that f of t is considered to be 0 for negative t. And those will be very important later when we consider shifts of this function to the right. So, in essence, what we're doing here is we are talking about functions that are different than the functions we used to look. So, for example, a function like cosine of t starts at 1, goes down to 0, negative 1, 0 again, and then it keeps going, oscillating between negative 1 and 1. But what's going on before 0 is this function should be considered to be identically 0. So this is a short introduction into the definition of the Laplace transform. In the next lecture, we'll look at how we can compute the Laplace transform and how can we circumvent this integration and develop a system of shortcuts for us to compute the Laplace transform easier and compute the inverse Laplace transform without much work. Thank you for listening, and I'll see you in the next video.